Uh, under 2.2 on page 15, we are going to understand something to do with functions and mapping. And as it is written there, a mapping transforms one set of numbers into a different set of numbers. The mapping can be described in words or through an algebraic equation. It can also be represented by a graph. And the bold statement there reads, a mapping is a function if every input has a distinct output. Function can either be one-to-one or many-to-one mapping. And I just want to explain what we mean by one-to-one. We may be having this is input, and there is an output there, or this could be the domain. The domain is the very original value of x, and the range is the solution after some operation. So when we have this A mapping to a specific value B, this is A to B, C to D, and E to F, then this is what we are calling one-to-one mapping. This is one-to-one mapping. And why one-to-one mapping? Because one value of an input maps to exactly one value of the output. A second example of mapping could be, let's talk of that and that. So we have that value mapping to that value mapping to that. This one is now many-to-one mapping. This is many-to-one mapping, many-to-one mapping. For example, if you may have if the rule of the game we have -2 there as an input and +2 there, and then the operation is x squared. When you square -2, it will give you a 4. When you square a +2, will give you a 4. So two inputs or many inputs can end up giving you one output. That is a function. But when we have a situation of this nature, that we have one-to-many, under one operation, it is not possible to have one input giving you different solutions if the function is the same. So there is no way if we have a +2 as an input and the operation is squared, this one is going to give you a 4 and this one is also going to give you a 4. So there is no way 2 squared will give you two different solutions. So this one is not a function. This one is not possible. It is not a function. Having done that, it is important to note that many mappings can be made into functions by changing the domain. And I just want to explain something. When you consider y is equals to the root of x, for all possible values of x, for all possible values, values of positive x, they will give you a specific value of y, because we have a square root of all positive numbers. But when we have negative x, we do not have the value of y, because we do not have the square root of negative numbers. Therefore, it is important that we can specify. It is important to specify what is the range of our domain. Because if you consider this one will only make sense that y is equals to the root of x only when x is greater than or equals to 0. It makes sense only when x is greater than or equals to 0. Or only when x is greater than or equals to 0. So when x is less than or is less than 0, it doesn't make sense because we don't have the square root of negative numbers. The pink pages down there reads, the domain is the set of all possible inputs for a mapping, while the range is the set of all possible outputs for the mapping. In other words, there is the input, and then there is operation, you know this in the function, and then there is the output. So with this, we know what is the domain, and we know what is the range. Domain is the input, and the range is the output. Having said that, I want us to say something to do with on page 16 before we go to example 7. It is written up there that if the domain were all the real values, the real numbers are, then the function y is equals to root x would not be function because values of x less than 0 would not be mapped anywhere. It is already shown in this graph that we will not have the value of y when x is less than 0 or it's having negative numbers. However, if you restrict the domain to talk about x is equals to greater than or equals to 0, if you restrict this domain now is now restricted because it can only assume specific values which are starting from 0 moving forward to the negative, to the positive direction. Then every element in the domain is mapped to exactly one element in the range. Of course, you can see whatever value of x, you can have the value of y. Whatever value of x, we have the value of y. Whatever value of x, we have the value of y. Such that when x is 1, y is 1. When x is 4, y is 2. When x is 9, the root of 9, y is 3. That is exactly what we mean. We can write this function together with its domain as the function of x is equals to the root of x with restriction where x is a real number and x is greater than or equals to 0. If you do not include this restriction, then it doesn't make sense. But when it is having restrictions, it makes all the sense. And that is what we need to carry on to example 7. The pink notation there, you can also write this function as, that is just a different writing of the function, whereby there is the function of x, and then the rest, the function of x is x, the root of x, and then the rest follows normally. You can write it anyway. So with that, let us see what we can do in the next video in example 7. Okay?